Okay, I'm going to continue talking about measuring perception and continue to move forward through these various kinds of measurements. If you remember from last time, we talked about some of the basic classical psychophysical methods. So the method of constant stimuli, the method of adjustment, and the method of limits. And we also talked about how we can use these to measure absolute threshold. And we also talked about difference threshold. So far we have just talked about the detection of stimuli and measuring this absolute threshold, which tells me when can I detect a particular stimulus. And that in itself is really interesting. I gave you some basics of human detection, that we can see, a candle from 30 miles away on a clear dark night or whatever. That's interesting. But those psychophysical methods also allow us to learn about the mechanisms responsible for experiences. And one example that we will talk about very soon, as we are talking about the eye, is the dark adaptation curve, and what this tells us about the mechanisms of the eye and how we adapt when it gets dark. So we all know, right? We've all had this experience of we walk into the outside in the dark, or we walk into a movie theater, let's say, when the lights are down. And when we first walk in, it's like this picture on the left, where if there's some kind of light behind something, we might be able to see it, but we can't really tell where we're walking, so we really have to just stop and wait. And as we wait, things start to look more and more like the picture on the right, where we can kind of see where we need to put our feet in order to get to the next step, and that takes time. Well, we learned about that dark adaptation curve because of one of those classical psychophysical methods, the method of adjustment. So people would start off in the light, but then we'd turn all the lights off, and we'd say, can you see this flashing test light? And they would turn down the knob lower and lower on that flashing test light until they could no longer see it. And so that was the method of adjustment, right? As they're turning this knob and just adjusting the light. And then we gave them time for their eyes to adjust, and they continued to, we could see them get more and more sensitive to that flashing test light, and their threshold went further and further down. And we learned about really dark adaptation and the mechanisms responsible, which we will talk about in the next chapter. So in this first chapter, he discusses 5 additional techniques for measuring perception. Clearly there are more. There are lots of different kinds of ways of getting information about brain activity. We're going to talk about olfactory receptor neurons firing and so forth. But as these basic kind of techniques, he starts out with, so we've done absolute threshold. What's the smallest amount of stimulus energy that I need to detect a stimulus? Difference threshold. If I have 2 stimuli, what's the smallest difference that I need to be able to distinguish that those 2 stimuli are different from each other? And now we're going to look at magnitude estimation, which is the question of how different are these stimuli? How different is a rock concert from rustling leaves or from neighborhood noise or whatever? What we know of subjective magnitude mostly comes from S.S. Stevens's work in the 1960s. He gave us this power law, and it is really refining some of what Fechner said about these magnitude estimations. But S.S. Stevens became much more specific about the formula and about the mathematics behind this power law, where perceived magnitude, we're going to call that P, so what the person is actually perceiving, equals some constant K multiplied by stimulus intensity, so whatever the standard stimulus was, raised to a power of n. Okay, said simply, our magnitude estimates are based on an exponential relationship instead of this more linear relationship that we saw with the difference threshold. And we can see both response compression and response compression depending on whether or not n raised to my power n, whether that n is less than 1 or greater than 1. And if you, again, really feel comfortable with the mathematics, I'm going to do a quick mathematic walk through the math on Monday just for those people. And if you don't like mathematics, you can put your fingers in your ears and ignore me or whatever. But I'm going to go ahead and give an example. So in Appendix C, he gives an example of response compression. He uses brightness. So the way these magnitude estimate studies would work is, let's just say I give you a standard stimulus. Okay, here's my basic stimulus, and I'm going to say this is 10 units. We're going to call this 10. And then I'm going to give you, I'm going to double that, triple that, and so forth. And I'm going to ask you, what are you going to estimate the intensity of this light to be, given that the original was 10. Okay, saying we can do the same with tones or with any sensory modality. Okay, his example from the book is for brightness, and it shows this kind of response compression where n is less than 1. So for example, when the intensity is 20, so people estimate this as perceived brightness is 28. And if we double that, so the stimulus intensity now, we know, has gone from 20 to 40 because we know we doubled it. The person might say the perceived brightness does not double to 56, which is 28 times 2. It increases only to 36. Okay, and in fact, for brightness, I think we need it to be something like 8 times as bright for us to say it's twice as bright. So we have this kind of response compression. Okay, because of this exponent, because of this power law, we can also see response expansion when n is greater than 1. And an example might be electric shock, where the exponent might be more like 2. Okay, so now we are again giving the standard stimulus. We're going to call this 20. We double that to 40. Okay, when we give them the standard stimulus of 20, their estimate, so what's your perceived stimulus? They say, let's just say 6. We double it to 40. Them doubling it, they would say it's 12, right? But instead, they say it's 49. This doubling of electric shock feels a lot worse. So we see this kind of real expansion, as that exponent is larger than 1, and we're going to see that kind of exponential rise. Okay, so I have a screen question at the end, which sometimes gets into really great conversations, sometimes really doesn't. And but I have why different power functions for different senses. And I am going to leave some silence here. And then I'm going to provide my understanding of what the answer is, but it doesn't mean it's the answer. So why do you think we see different power functions for different senses? One thing I hear from students a lot is that we want that kind of response expansion for something like electric shock that's going to cause us pain, because pain tells us that something's dangerous. And so if it's getting worse, we want it to have that kind of exponential effect of feeling a lot worse. What I usually I'm trying to get them to come to, and sometimes we get off on some evolutionary discussions of evolution. What I'm trying to really get people to come to is this realization that it depends on the stimulus from the environment. And again, these are my assumptions, but I would assume that something like light, so when we are in a dark area and we want to be able to see something in front of us and maybe read a piece of paper that has very little, is under a very low light level, we need to be able to see that as well as we can, but we need to still be able to walk out into the sunshine where, you know, we have actually 10,000 times as much light or whatever, and not be blinded. So there's this real kind of protection in our sensory systems that has evolved. And I assume we would see this in other species as well, the same kind of response compression for the same things we have response compression for, and response expansion for the same kinds of things other animals have response expansion for, because it does make sense evolutionarily given the information from the sensory modality. Another additional technique he talks about in this early chapter is recognition. So if you remember early on, I talked about how in that perceptual process we want to distinguish between perception and recognition. So we might actually just have somebody name an object. So we put the picture up that's on the right, and we want them to say duck, basically, or that is a duck. And we measure that naming time, or we just make sure that they have the category correct. And what we're looking for is categorization. Can they categorize the object, and are they recognizing it? Reaction time is another technique for measuring perception. So with that previous study measuring recognition, we might go beyond just measuring can they categorize it, do they get it correct, when we might look at reaction time. I'm showing here the results and a study that is based on a kind of Posner type study where they have you look at the fixation cross. So that fixation cross that's in the center, you're putting your eyes on that, and you're going to tell me when a particular target comes on the screen. And they sometimes have a kind of dark bar that for the most part is when that dark bar comes up, let's say at the top of A, the target is going to come up at the top of A. Okay, and what they find is when you're looking at the center of the screen and the dark bar comes up at the top of A, and then the target comes up at A, you can see the reaction time below that we are faster to say, yes, I see the target, than if the dark bar comes up at A. So we've kind of put, as we're going to talk about it in attention, we kind of put our spotlight of attention, even though we're looking at the fixation cross, we're really kind of attending up at A. If the target comes up at B, people are almost 100 milliseconds slower to see that target or detect that target. Another technique is just description, which is more of a phenomenological report, asking people what do they see, which is a more qualitative measure. I usually do this in class and ask people, what do you see in A? And for most of us in psychology, this really ubiquitous ambiguity, visual ambiguity, for me, I go back and forth very quickly between the faces and the vase, and it's a little bit frustrating actually, and I think it's just because I've seen it so many times, but oftentimes people will see the vase or see the faces. We're always going back and forth. We never see both at the same time, but some people get really kind of stuck in one interpretation. And in B, I get different reports from students about tic-tac-toe boards and 9 boxes and so forth. But what I'm kind of looking for, if you look at B, you will notice that at the intersections of those black boxes, there are these kinds of darker squares, these kind of gray ghosts, as they are called. And if you move your eye to that actual intersection, it goes away. And you can see that gray ghost in the other intersections that you are not fixating on. We are actually going to explain why that happens in a later chapter or in a later lecture. So that's a more phenomenological report. I'm just asking you to describe what you see. The final one he talks about here, the final technique, is having people perform actual physical tasks or make judgments. Those kind of belong to two separate categories in my mind, but it doesn't really matter. This first example is definitely a physical task, which involves a judgment. So we can have people, and we're going to see this in the taking action chapter, where they show people a distant target stimulus in the field. Then they have the person close their eyes and walk and try to stop when they get to the target, okay, as accurately as possible. And people will get pretty close to the target. And we can even have people walk a few steps to the left and then try to estimate. So all of this with their eyes closed, and they're still pretty good at estimating where that target is. And you can see that that judgment is that they're making a judgment, but we're taking that into account with their physical task. Another example is that they've had people look at a particular hill and estimate the steepness of that hill. And they've had people do this either just as they are, or I think maybe wearing a light backpack with nothing in it, versus wearing a heavy backpack that is going to weigh them down quite a bit. And the people with the heavy backpack, they estimate that hill as being steeper than the people who have a light backpack, as that kind of effort is taken into account when they're making their judgment of the steepness of the hill. So that's just another technique for measuring perception. So Goldstein has taken signal detection theory out of Chapter 1 and put it into Appendix D. And over the years, I have talked about this less and less and explained it less and less. And I really don't, I'm okay with that. But if you have any questions or are at all interested in signal detection theory, it makes some very good points, some very important changes in methodology are taken into consideration. So originally, if we look at those classic psychophysical methods that we saw from Fechner, there are some problems with that. If you remember, Fechner always had a stimulus that was being presented, and sometimes it was below threshold and sometimes it was well above threshold. And he was measuring absolute threshold. And for what he was doing, for measuring absolute threshold, when they were measuring difference thresholds, they were averaging across many, many people. And so a lot of this didn't really matter. But sometimes we want to know about individual differences. Really, these questions came about in the 1940s when we were starting to try to apply some of these psychological theories and hypotheses and methods to things like people who were looking at radars and whether or not they detected some enemy blip, whether they were confusing enemy blips with friendly blips, or whether they weren't really catching that blip at all. When we're looking at an individual and we're measuring absolute threshold, we have to realize that there are a number of things involved that make this much more complicated than just, are we getting at their absolute threshold if the stimulus is always present? First of all, people differ in their motivation. So do I want to, am I taking a hearing test because I hate missing things that people are saying, and so my motivation is that I really want to make sure that I hear something before I say I hear something? Or am I taking a hearing test because my daughter or granddaughter is making me take this hearing test because they think I don't hear them and I don't want a hearing aid? So that motivation is going to mean a really different kind of where I'm placing my threshold in all of that. In addition, there's always noise. There is noise in the environment. There is noise in the system. There's always neural firing. So there's this kind of internal noise. And so there's always this uncertainty. And because there is this uncertainty and these differences in motivation and this noise, sometimes if we're looking at an individual and that we do use these same kind of methods for measuring now, for hearing tests, if we're using these kinds of methods for an individual, we have to realize all of these problems with that kind of classic psychophysical approach. So signal detection theory was introduced, if I remember correctly, in the mid-1940s. So if I want to measure an individual's absolute threshold, so I want to know whether or not someone needs a hearing aid, I really probably don't want to use Fechner's classic psychophysical methods because we know that people's motivation differs so much. So with a signal detection kind of method, now the stimulus is not always present. Okay, we're going to choose some stimulus strength that we think is right around their absolute threshold, and sometimes it's going to be present and sometimes it's going to be absent. We know that noise is always there, that they always have this uncertainty and they have differences in motivation. So we're going to see 4 possible outcomes. So if the signal is present and I correctly say, yes, I hear that, I'm just going to stay with the hearing example, that's going to be called a hit. If the stimulus is present and I miss it, that's going to be called a miss. So I say I don't hear anything. That's a miss. All of these names make a lot of sense. If the signal is absent and I think I hear something, so I say, yes, I hear that, that's going to be called a false alarm. And if the signal is absent and I correctly say, I don't hear anything, that's called a correct rejection. Okay, and now we can look at the proportion of hits to false alarms, and we can see something about the response bias of the perceiver. So this is their response criterion of what is their motivation and where are they in this kind of how much do I want this hearing aid, basically. And we can manipulate that motivation with people sometimes, but what this proportion of hits to false alarms gives us is a better idea of their absolute threshold. And if we can find a way to manipulate that response criterion, we can get a better idea. So sometimes they do this with offering, in studies, they do this with offering money to people and changing the outcomes. We can get a better idea of their actual absolute threshold. So typically I'm pretty bad about putting up these summaries, and when I do, I try to get students to tell me their summary of what we talked about. But just as generally, I think overall now with measuring sensation and perception, we talked about absolute threshold, difference threshold as some actual basic measures that we're going to continue to take that tell us not just about those thresholds, but about mechanisms behind sensation and perception. We talked about the 3 classic psychophysical methods that really came from Fechner, method of limits, method of adjustment, and method of constant stimuli. Goldstein goes through 5 additional techniques, although again, I think there are more that we are going to continue to just address because we will talk about measuring brain activity and looking at brain activity in different ways and looking at just sensory neurons firing in different ways. But basically, I think there are actually a few more, but basically magnitude estimation, naming, reaction time, phenomenological report, physical tasks, asking people to actually do those tasks which involve judgments or just asking for the judgments themselves. And then very briefly, I went over signal detection theory, which you can completely wipe that out of your memory if you want to, or you can come to my office and ask me to go through that more thoroughly if you want to, or ask me online. But do warn me ahead of time. It really has been years since I've gone through the specifics of signal detection theory, and I have heard it explained by several different professors and different textbook authors, and there's a way to explain it that makes the most sense. So let me know ahead of time if you want that.